All right, so in all these problems, what you need to do is you need to go through and read the problems carefully, and then write down the things that you know, the variables that are given, and make sure that you get the proper variable names listed. And then you will really have two equations when you're dealing with kinematics problems. And I think by now you guys can pick out, what is a kinematics problem where you use those, because you're going to be looking for things like position or velocity or acceleration, or in this case, we're looking for angle, which is another word for angular position or your angular displacement. Um, so as we go through here, we have a time of 3.2 seconds. It says that it's at constant acceleration, but it doesn't give that acceleration. But it says that it turns at a rate of 2.51 times 10 to the fourth revolutions per minute. Which variable is that? If I have something in revolutions per minute, what is that? Revolutions per minute rather. What is what is that variable? Remember, we have theta, omega, and alpha. Theta for angular position, omega for angular velocity, and alpha for angular acceleration. So which is this one? It's what now? It's omega, right? Omega is our angular velocity. Remember, omega is sort of that curly looking W. It's the lowercase omega. And we want to know the drill's angular acceleration. That's going to be alpha. We want to know what alpha is. And then we also want to know the angle. Which variable is that? Looking for the angle. That's going to be our variable theta. So we want to know our variable theta. Uh, we wanted to know it in radians, so that should clue us in that we need to convert our our angular velocity here into radians, and we'll go ahead and convert it into radians per second. Now, with kinematics problems, you don't necessarily have to convert their units. So if we wanted to convert this to, say, revolutions per second, because one of our times is in seconds, then we could work through it in revolutions per second, and our answer would come out in revolutions and not radians. But since it's asking for the angle in radians, let's go ahead and convert this. I need two conversion factors. I know that in 1 minute there are 60 seconds. And notice that gets rid of the minutes and leaves me with revolutions per second. And then I know that in one revolution, there are how many radians? There are 2 pi radians. Remember your unit circle. As I go through my unit circle, I go from 0 to pi over 2 to pi to 3 pi over 2 to 2 pi. So in one full circle, there are 2 pi radians. It'll help you to know your unit circle for the next test, to be familiar with it. So 2 pi, that's going to be 2 point, what's that, 25,100 divided by 60 times 2 times pi. I get 2630. That's in radians per second. Okay, so now our next step, we have everything that we know and everything that we don't know. Actually, no, there is one thing that we know that I haven't listed yet. What is that? Not everybody at once. What is it? Right, the initial velocity. This came up in chapter 2, but when it says that it's at rest, that tells me what my omega naught is. It's often 0, but not necessarily always 0. So my omega naught is equal to 0. Now, I always like to write my equations. I only have 2, so they're pretty easy to write. And they're on your equation sheet, but I like to write them. I say theta equals omega naught t plus 1 half alpha t squared. And then I also have omega equals omega naught plus alpha t. Now at this point, I don't really know how I'm going to approach this problem, but I know that I'll need to take the information that's given and in some way solve these equations in order to find what I'm looking for. Now I'm looking for alpha here and theta here. And I don't know, well gosh, what don't I know? I don't know alpha, and I don't know theta. Here, I don't know alpha, and I think that's the only thing that I don't know here, right? So I don't know alpha here. So I can take this equation and solve it for alpha. And I say alpha equals omega minus omega naught divided by t, and that gives me 2630 minus 0 radians per second divided by the time that's given, which is 3.20 seconds. And then I get an equation, or I get a value for my alpha. I get 820 radians per second squared. And then I can go in, take this value, plug it in here. I know everything else, and I can figure out now what is theta. So I say theta equals omega naught t. Omega naught is equal to 0, so this whole term goes away, plus 1/2 alpha t squared. That's 1/2 of 820 radians per second squared times our t squared, which was 3.2 seconds squared, and that gives me 410 times 320 squared, 3.2 squared. I get 4,200 radians. All right. On your test, you'll have a similar question, something like this, maybe two-step, probably not a substitution problem where we have to solve a system of equations. You'll see that elsewhere on the test, but probably not here. Okay? Okay with these, I think? Right. Largely just reading the problems and being familiar sort of with how we talk about rotational motion and being able to find these various quantities. Let's go on into chapter 8, unless there are there any pressing questions about chapter 7. Now, we're not leaving chapter 7 because chapter 8 is closely paired with chapter 7. And in fact, we'll see some similar kinematics questions come up in chapter 8. But they'll come up in the context of Newton's second law, where we have to use Newton's second law to find the acceleration, and then we can tell other things about the motion. So if you haven't gotten this yet, that's okay. We'll come back to it. Now, we're not really coming back to centripetal forces, so make sure that you're up on that. Remember, with centripetal forces, I have this force that causes circular motion, and sometimes that force is something, and sometimes it's another thing. So, for example, we talked about several examples like the gravitron thing, or what's it called, a centrifuge, something that spins around. The centripetal force is like the normal force pushing against your back. A rope, a ball and a rope is the tension is the centripetal force. And remember that centripetal force is equal to mv squared over r. Now there's some homework problems to help you with that. We did some examples in class as well. So if you have trouble with centripetal force, any questions about centripetal force right now? Well, as you're reviewing over it, I would look over it in the next couple of days while it's still sort of fresh, both the kinematics and the centripetal force problems. And if you have questions about it, come see me or we can talk about it in class even. Well, let's go on to chapter 8. Okay, so we're going to see, many of you won't take Calc 3. Actually, do you chem majors take Calc 3? You do, right, yeah. So I'm not sure if your engineering majors do. Geomatics, you do take it. Geomatics do not, I don't think, right? We've already done some Calculus 3 stuff. We've done the dot product. Calculus 3 is generally vector calculus, and sometimes it's also multivariable calculus. That is when you're integrating over multiple variables, say over x, y, and z. We're going to do both of that in this chapter 8. We're also going to see the cross product, which is right here. As I said, we've seen the dot product, which was called the scalar product, where you take the product of two vectors that are in the same direction. So you take one vector, the component of it that's in the same direction as another vector, and then you can multiply those two. We use that to find work. The dot product can be used for other things too. But now we're going to see the cross product. And the cross product is when you take one vector that's perpendicular to another vector, and you take the product of those two vectors. The cross product is also called the vector product. Now remember, the dot product was called the scalar product, and the result of the dot product was a scalar quantity. So what do you think the result of the cross product is going to be? A scalar or a vector? A vector, right. So the result of the cross product will be a vector. It is the product of two vectors. And the result of the cross product is orthogonal to both of the vectors. So let's say that we have a vector A like this, a vector B that's in this direction. What is a vector, or what is the direction of a vector that's orthogonal to both A and B? Let's test your vocabulary. Do you know what orthogonal means, first of all? Most people do not. It means what, Kim? It means perpendicular, right. Orthogonal is just a fancy word that means perpendicular. In this case, it's going to be perpendicular to both of these vectors. What is the direction of a vector that's perpendicular to both of these vectors, or it's orthogonal to them? Right, along the z-axis. So if A is in the x direction, B is in the y direction, then the resultant is going to be in the z direction. So our cross product, A cross B, will be in the z direction. It's going to turn out it's actually going to be in the positive z direction, but we'll see how to figure that out later. Um, so the magnitude of the cross product is equal to the area of the parallelogram that's bordered by the two vectors. So here's a diagram here. I have a vector A. Notice this vector is in the positive x direction. This vector B is sort of in the negative z direction. And then my cross product, A cross B, is orthogonal to that. But we can determine the area of this, or excuse me, the magnitude of this vector A cross B is going to be equal to the area of this parallelogram. You don't really need to know this as far as it being the area of the parallelogram, but we do need to know how to determine the magnitude of the cross product. And that actually turns out to be quite simple because that area of the parallelogram is just equal to AB sine theta. So the area of the parallelogram, which is, this quantity here, is equal to the base times the height, which is equal to AB sine theta, or BA sine theta. So if I were to write A cross B, the cross product of vectors A and B, the magnitude of this is equal to AB times sine of theta. Oh, so here, AB sine theta. Notice that I've written the magnitude of A and the magnitude of B. I've written that by leaving the little arrows off the top. So I just take whatever the magnitude of this vector and the magnitude of this vector, and then the angle between them. So if I draw A and I draw B, draw B like this, the angle will just be the angle between those vectors. Okay? We'll see that come up as we're using cross products to determine the value of the torque. That we'll need to look for the angle between the two vectors that I'm doing my cross product for. Y'all with me so far? I'm going to throw out some new words for you. And the cross product, initially it looks complicated, but it's really not that complicated. Once you do it a few times, and you'll do it on the test too, so hopefully that'll be an easy, I don't know, 5 to 10 points for you. It has several applications in physics. If you take any fluids courses, it comes up a lot in fluids as you deal with gradients and curl, and some of you engineering majors will certainly see that in your upper level courses. But in this class, we're going to use it to find torques, because in torques, when we're determining the torque, we'll need to take the component of one vector that's perpendicular to another vector and multiply those two. And so we'll use the cross product for that. Now let's do an example of a cross product. As I said, you'll have to do a cross product on the test for certain. I'll just give you two generic cross products, and then we'll do one with numbers in it. So one with variables first. Let's say that I have two vectors, AX in the I direction, plus AY the j direction, and then bx in the I direction, plus by in the j direction. You can also have a k, but we'll just leave out the k for now. But you'll see k variables in some of your problems. We'll do some in the next chapter. Now, if I do FOIL on this, or if I just write it out, I get ax plus ay in the I and j directions crossed with bx plus by. Oops, excuse me. Forget my unit vectors. Remember, the unit vector just tells the direction of that vector, so I've broken the vector into its magnitude and its direction. Unit vector has a value of 1. You need to be careful when you're doing your cross products, because A cross B is not equal to B cross A. So I have to make sure that I get these in the right order. If you don't get them in the right order, the answer will not come out correctly. So just remember that A cross B is not equal to B cross A. And so I can't switch these two. I can't switch the places of these two and still get the correct answer. Now I can do FOIL to expand this out. It's going to be, well, first outer, inner, last. So, AX, BX, I cross I. Outer is AX, BY, I cross J. What's inner? AY, BX, J cross I. I'm being careful to get my quantities correct here. So, for example, here, when I do inner, I have to do j cross I, not I cross j. So as you're going through and doing your cross product, just be careful that you get the right order of your unit vectors within it. Also, what do you think the cross product of I cross I is? Now remember, the cross product at its very basic form is the product of two vectors that are perpendicular to one another. So what would you think then the cross product, don't say it out loud right yet, what do you think the cross product of I cross I is? Yeah, that's a good guess. It's not right though. Not right too either. All right. What do you think the cross product of I cross I is? If the cross product is the product of two vectors that are perpendicular, I and I are they perpendicular? No, they're parallel to one another. So what do you think the cross product is? It's going to be 0. In fact, we could go back. If you think about our magnitude, remember our magnitude was AB sine theta. What is the angle between I and I? It's 0 degrees. And what is the sine of 0? It's 0, right. So the cosine of 0 is 1, but the sine of 0 is 0. Okay, so our like terms are going to cancel out. Let's see, we had one last term, the L in FOIL, which is AY, BY, J cross J. I didn't really need to write out all of these, though, because, as we just said, these terms go away and these terms go away, because anytime I have two parallel vectors or anti-parallel vectors, their cross product is going to be 0, because the angle between them is 0. That's what cross products do. They take the product of two perpendicular vectors, not parallel vectors. The cross product of a parallel vector is 0. We're also going to use the right-hand rule here in order to determine the direction of cross products. And we'll use the right-hand rule a lot next semester, too, when we do magnetic fields. It comes up quite a bit. We use the right-hand rule to help us understand the direction of orthogonal vectors. Orthogonal vectors in a right-handed coordinate system. Did you know that we live in a right-handed coordinate system? Did you know that? It's a convention that we use. Some people use left-handed coordinate systems, and that's okay, I guess. But typically, people use a right-handed coordinate system. All right? So the way you do this, there are a couple different ways. You can let your first finger, if you want to know the direction of A cross B, You let your index finger, your pointer finger, to be the first vector, A, your middle finger, you know, the rude finger that people use, your middle finger to be the second vector, and then your thumb will give the direction of the resultant, or the cross product of those two vectors. That's an orthogonal system where I have two vectors and then my thumb is an orthogonal vector to those two. But notice there's another vector that's also orthogonal, which would be, you know, if I had a thumb coming out this side. There really is only one answer, though, to what is A cross B, and we can use our right-hand rule to figure out what that is. If you're in Calc 3, you'll do this in a slightly different way with matrices, and it looks a little fancier. But this is a surefire way to help you determine the direction of A cross B. All right. So let in the index finger of your right hand go in the direction of the first vector, and the middle finger of your right hand go in the direction of the second vector. You have to use your right hand, though, because sometimes students will use your left hand. And I've seen students sort of fits around with their left hand in the exam, and sometimes I try to go by and tell them, you know, hey, don't forget you need to use your right hand, not your left hand. My physics teacher in high school, she always said that you should carry two things in your back pocket. She said you should use a test charge, like always carry a test charge in your back pocket. We'll deal with that next semester. But she also said that you should always carry your right hand in your back pocket. That way, if you ever need it, you'll have it for the right hand rule, for like a quick draw. Okay, did you see how I did that? And then I'm ready to do the right hand rule. Okay? So make sure you always use your right hand. Don't use your left hand. And then when you do that, the thumb of your right hand gives the direction of the cross product. All right, let's see. Do I have an example? Oh, so if I want to know I cross I always like to draw my coordinate system. This is I, this is J, and this is K. I know I cross I. Gosh, what does I cross I equal to? 0. Two parallel vectors, the cross product 0. Similarly for J cross J, those are both equal to 0. Now, I cross J and J cross I. Let y'all do this, index finger, go in the direction of I, and then your middle finger in the direction of J, and then what direction does your thumb point? It's got to be K, either plus or minus K, right, because K is the only vector that's perpendicular to I and J. But is it plus or is it minus K for I cross J? Well, don't be afraid. I know you're sort of, I don't want anybody to see me doing this. Which is it? Is it plus or minus K? Some people say plus, minus. All right, let's see. So I, J, and then my thumb comes out of the board. Is that plus or minus K out of the board? That is plus K, right. So I cross J is equal to plus K. And remember how we write the plus K vector as a symbol, that we use this symbol, or sometimes it's just a dot. What is that supposed to represent? An arrow coming straight at your head, okay? So that's I cross J. What is J cross I? Well, you can probably think about it. I know that I cross J is not equal to J cross I. And I also know that the product of I cross J has to be in the K direction, either the plus or minus K direction. So what do you think it is? It's got to be negative K. We can do a right-hand rule and just figure that out. J, excuse me, I, and now my thumb points into the page. See how I did that? If I do I cross J, it's like that. If I do J cross I, it's like that. You see that? All right. So J cross I is equal to negative K. That brings us to one of our, oh, and then the symbol for that looks like this, or sometimes it's just an X. in the negative k direction. We've seen that before, and we'll use it more next semester, but we'll see it here now. Okay, so, oh, and that brings up one of our properties of cross products is that A cross B is equal to the negative of B cross A. What is that property? It's not commutative. Is that the right property? I always forget the names. The commutative property is that like AB equals BA. Isn't that commutative? Am I right? I don't know either. It doesn't really matter. But with numbers, we can just switch up their order, but you can't do that with cross products. In fact, if I switch the order, it's the negative of what it was because of this whole thing with our right-hand rule and stuff. Okay, so then our cross product becomes, we go back to what we did for FOIL, it becomes AXBY K minus AYBXK. Or I could just say AXBY minus AYBX in the K direction. All right. We can also extend this to 3 dimensions where you do, well, let's do an example with 3 dimensions. So let's say that my vector A is equal to 3I plus 2j, and my vector B is equal to 2j, or no, let's do 4j minus 1k. And now I want to know what is the cross product of these two vectors. So I'll give you a few minutes. I want you to write it out. You need to do FOIL and then figure out what is the various directions of your cross products, uh, I cross J cross K, all that jazz. So I want to know what is the product A cross B. What is the product of A cross B? You can do FOIL, but remember you don't have to write out all of FOIL because anytime I have two parallel vectors, that cross product is 0. So you can just write out those that are perpendicular to one another, of which there are only a few. All right, I'm going to start expanding this out. I have 3 times 4, that's 12 I cross j. I have j cross j. Do I need to include that? The 8j, not going to include that because j cross j is 0. Oh, that was enter. I skipped O. Minus 3I cross k. Being careful to keep the order correct. And what's my last one? Minus 2j cross k. All right. Now I know what I cross j is. We already did that. What was I cross j? K, right. But I have these new ones that I haven't seen before, the I cross K and the J cross K. But no need to fret. We can draw our coordinate system over to the side. I always do this because I don't memorize these. In fact, there are so many combinations I wouldn't bother memorizing them. But just use your right-hand rule. So if I want to know I cross K, I, and then K is like this. So what is the direction of I cross K? Negative j. I know it has to be something j, positive or negative j. And so this one's going to be I cross k will be negative j. So I have 12k minus 3 negative j. And then j cross k, First of all, I know that's going to be plus or minus I, right? Because it has to be orthogonal to j and k. But what is it? Is it plus I or minus I? Take a moment, use your right hand rule, index finger in the direction of j, middle finger in the direction of k, and then your thumb will point in which direction. Use your right hand. Use your right hand, okay? J, positive I, right? Because my thumb is pointing in the positive I direction. So that's going to be minus 2I. So the resultant of this is going to be minus 2I plus 3j plus 12k equals A cross B. All right, we'll do some more examples, and we'll also do some examples later where we find the magnitude. Remember the magnitude of A cross B. I'm not going to do it here, but we'll do it later. The magnitude of A cross B is the magnitude of A times the magnitude of B times the sine of the angle theta. We won't do angles between vectors in 3 dimensions. They get a little hairy. You geomatics guys, you must do 3-dimensional vectors, right? Do 3-dimensional vectors, geomatics? Yeah. We're not going to get into it in that sense, but we'll deal with 3-dimensional vectors in this way. And we will do angles between 2D vectors, which we've done before in chapter, 3 or whatever. All right. But right now, let's move on to applying this in torques. And you'll see uh, why the cross product becomes so useful. But as I said, you engineering students, you'll see it again in some of your fluids classes as you deal with rotational things, fluids rotating and turbulence and the like. All right, so when you think of torques, what do you think of? I know what I think of, but what do y'all think of when you think of torques? What? A hammer? Seriously? Uh-huh. Oh, good. Yeah, he's right, that you get more torque if you hold it at the end. I always think of a torque wrench. You ever seen a torque wrench? No, or I think of a cheater pipe. You ever use a cheater pipe? Right, you have a wrench and you have a nut that you're trying to get off and you can't get it off, so you say, what do? Well, you pull out your cheater pipe because everybody has like a pipe about this long in their shed that when they can't get a nut off, they put it on the end of the wrench and then you pull it and it allows you to get the nut off more easily or loosen the bolt. Okay, the cheater pipe depends, I guess. But anyway, when I think of torques, uh, torques cause rotational motion. And it's useful to describe torques because, uh, well, whenever we have things that are rotating in a rotational sense, that's caused by a torque. So Newton's second law also extends to torques. And just like forces cause acceleration, torques cause angular acceleration. So we can sort of think of torque as an angular force. In fact, we'll treat it very much like that. So remember, we have these analogs between linear and rotational motion. We said that theta was not the same as, but it's similar to x. That omega is similar to v, the linear velocity. That alpha is similar to the acceleration. And now we're going to say that torque is similar to the force. Uh, So we can think of our torque now as a type of angular force, and we can find the torque with the cross product. Now we have two things at work when we're talking about torques. We have the force, this is the applied force, and then we also have the moment arm. This distance is the moment arm. The moment arm extends from the axis of rotation to where the force is applied. It is a vector quantity, and so we'll need to know it in vector form. And notice here that this vector, which is drawn as an arrow, this is the axis of rotation, and it extends down to where the force is applied. This is the angle that's between those two vectors, and it's given as an angle theta. Now, our torque is our cross product. It's equal to R cross F. Note again that R cross F is not the same as F cross R. We saw that with cross products, that those two are not equal. In fact, they're the opposite of one another. So whenever you're doing your cross product for torques, make sure that you get the R and the F in the right position. And then the magnitude of the torque is equal to RF sine theta. These are just properties of our cross product, but they come into play here. So on your test, you're going to have some questions. I'll give you the torque, and I'll give you the R vector and the F vector, and you'll have to figure out what is the torque. And then you'll have some other stuff associated with that, dealing with Newton's second law. But you'll have to know how to do the cross product. When the angle between F and R is 90 degrees, then the torque is, well, if our torque is RF sine of theta, what is the sine of 90? It's equal to 1. Oh, goodness. Got it okay, Asia? Okay, so if this is 90, then the sine of 90 is equal to 1, and so the torque is just equal to R times F. So if I have my R vector in this direction and my force in this direction, the angle between them is 90 degrees, then our torque is equal to R times F. This is what you did in lab. You remember the lab where you had the meter stick that was balanced and you had to put different masses on the sides of the meter stick? Right, you're dealing with torques, and in that case, you're dealing with torques that were at 90 degrees to the moment arm, or the force was 90 degrees to the moment arm, which allowed you to leave out the angle because the sine of 90 is 1. That's why it was so important in that lab that you keep the meter stick level. Remember, you had to make sure that it was level, because you can find equilibrium situations where it's not level, like this, but then your torques become a little more complicated. The SI unit for torque is the Newton meter. This is not the same as for work. So if you remember, we use joules for work, but a lot of people use Newton meters for work. But these are different. They're completely different, not related in any way, even though they have the same units. Clockwise torques are negative, and counterclockwise torques are positive. All right, you'll likely have a question. It'll be embedded with a different question like this one, where you have to find the net torque. And what I mean by that is I have several forces that are acting on this object. This object is allowed to rotate about point C. So this object you can think of as a rod, or I like to hold my pencil up to the page and think of this object rotating about this point. What I want you to do now is figure out what is the net torque that's acting upon this bar. I'm going to give you a little bit of guidance. You're going to ask yourself several questions. First of all, if I'm allowed to rotate about the point C right here, one or more of these forces will provide no torque at all. Which of those forces will provide no torque at all? Is it the 25 Newton force, the 30 Newton force, or the 20 Newton force? Why the 30 Newton force? Because it's at the axis of rotation, right? It would be like me trying to open this door by pushing right here. Right? I'm never going to open this door. I can never cause a torque applying the force to the axis of rotation. Tyler? Right, you would just ignore that force because it provides no torque. And then the second question you want to ask yourself is, which of these torques provides a negative and which of these torques provides a positive torque? So does this force cause the system to rotate clockwise or counterclockwise? Well, let's see. I always like to hold up my pencil and I imagine this force, and it pulls down, and that causes counterclockwise motion. And then this force, does it cause clockwise or counterclockwise? This one causes clockwise because it pulls down in this direction. Now notice if I move my axis of rotation, then it can change. Like if I put my axis of rotation over here, then this force doesn't cause any torque. So I have then, what we've done so far is we said this force does no torque. This force on the left does, what do we say, that's positive torque because it's counterclockwise. And this torque is negative because it's clockwise. Now what I want you to do, I'll leave you for the rest of it. You want to figure out what is the total torque. So you need to figure out the torque caused by this force and the torque caused by this force, and then take the appropriate sum or difference, however that is. You'll need to find your moment arm for each of them. That's the distance from where the force is applied to the axis of rotation. When you find your answer, if it's positive, it's counterclockwise. If it's negative, it's clockwise. Remember that one of these forces causes a negative torque. All right, let's just do maybe 15 more seconds, okay? We're getting close to the end of class. We'll stop at 340, 340. 340. Okay, awesome. I think C is right. The way we do this, I'll call this torque 1, and I'll call this torque 2. Torque 1, the magnitude of it is 25 times 2 meters, that's 25 newtons, times 2 meters, times the sine of 45 degrees. And then torque 2 is equal to 20 newtons times 2 meters. 2 meters because that's this distance, times sine of 20. And then if I say torque 1 minus torque 2, I'm subtracting them because of this negative. I get 22, positive 22 Newton meters. Because it's positive, that means it's counterclockwise. All right, we'll do some more problems like that next time. But you'll likely, you will see stuff like that on the test. You'll see cross products, and then you'll also see this type problem where you have a system with different forces acting upon it. Okay, now I'm going to hand out your test. If you didn't get your bubble form or take home at the beginning, I know a couple of you came in a few minutes late, I have them here, so please drop by. On the top of this test, it just has the number missed in the free response. So that doesn't include all the points for your test. All right, if you have questions about that grading, just let me know. This is in alphabetical order, so just come on up and you can go. That's Hillary, Zane, Alyssa and Paige, Alex, Kyle, Tyler, Mark, Frankie, Elena, Doyle, Brennan,